So, all right. So we're gonna go through a couple of different examples of ROP, starting with basically all-in program and working our way into incorporating libc by leaking it, and then fully into libc. So what we have to start off with is a very simple main. This is not even trying to hide the fact that it's vulnerable. This is just as a demonstration, right? Most challenges are going to be a lot more covert about where their vulnerabilities are. I'm literally telling you, now overflow with this next command. So this is just for the sake of demonstration. So what we see here is, first of all, if we run this, we get date back, and we have an address. So if we try and look at address 0, right, that's not mapped, and it's segfault. So how do we want to start this? Well, we know, from looking at source or just by looking at the imports in Binja, we have system. Obviously, a very nice place to start. So we have system, but we need something to pass the system that we can sort of control, right? We have bin date right now from the showtime function, and that's just a constant. There's no switch case that we can jump into like there was in a homework week or so ago, I believe. We will need to figure out a way to set RDI ourselves with our own value. So we're going to use ROP to do this. In this case, I didn't actually put bin sh anywhere in this binary or the string sh null byte, so we're actually just going to use the add trick because why not? We'll see it in action because it's fun. So first things first, we need to figure out our normal. Oh, and actually, I believe I forgot to compile this. Yes, let's see. Protector. All right, now this should be a little bit more exploitable. So we need to know how big our stack is, right? Just because if we look at source again, just as a need, we have 32 bytes of a buffer that we're going to need to fill up before we can start affecting the saved base pointer or the saved instruction pointer, right? ROP is still based around the idea of controlling the instruction pointer, but going even further to set up all these fake stack frames above it to do things for us. So we need to fill up 32 bytes, and then we'll be able to begin setting up our chain. Let me also really quickly copy this new binary out without stack protectors into Binja, so we have the correct binary over here. All right, that looks better. So let's get started. I'm going to do all this in a Python script, again, with Pwn tools, because, like Josh said, if you're still hard coding in manually encoded addresses, it's time to move on, especially because basically all the exploits from here on out are going to depend based on some output that the program gives you, right? These all are going to have to use libc to some extent, which, as we talked about, jumps around in memory. So you're going to need to leak libc to figure out where it is in memory and then use that value in your exploit. So you can't hard code that, right? Because that's changing every run. So, everybody needs to get used to this if you haven't been using it already. So rop1.py from import star and create our process of main, if we can type, and make sure we put an interactive at the end so that we don't lose anything. So usually what I like to do when I'm building up a big ROP chain is actually just create everything just as a long list of string concatenations in Python, because it makes it a lot easier to read. When you have these potentially really long ROP chains, these might easily wrap this screen 2 or 3 times if you put it all in one line, and it makes it just a lot easier to kind of see the logical groupings of what you're doing in the chain. Because again, some of these chains could be setting up a new syscall and then jumping, pulling something else out from the stack and then jumping into libc, and so you would be able to break that up into its components a lot easier. So we know we have 32 A's to fill to get to the end, and I'm going to go ahead and actually just bump that up to 40 because we know we also need to overwrite the saved base pointer. So at this point, the next data that we have, or the next values that we put in, should be overwriting our saved instruction pointer. So what do we want to jump to? Well, we need to put something into RDI that when you call system then, RDI is interpreted right as a string pointer, and then that command is executed. Like I said, and like Josh showed, the string ed nullbyte happens to show up in basically all programs. So we're going to use that again because I don't want to work on, we'll get to leaking libc after this, and binsh is all over the place in there, but for now, it's a reliable way to do it. So let's go to the hex editor and find ed nullbyte. You need to do that. Okay, I know it's in here, I just saw it earlier. Fine, ed, where was it? That's not hex. Next, oh, there it is. So right here at file offset hex 1975. Is there a shortcut to go to file offset in Minja? I forget if there's. Okay. Wonderful. Let's look for just the raw string ed then. Okay, that's. You need to select to find it? No.
No, you have it on the wrong mode for search. Control F. Skip string.
But it's a. Okay.
It just G and then like four times.
Yeah. Well, so as we okay. Yeah. Exactly. Yeah. Here it is. Oh no, those are the symbols. Are they just not being loaded in Binja?
No, I've seen it
I don't see them here. Interesting. Okay. Well, this trick should work. In this case, let's just do it the easy way and open this up in GDB. Let's just break on main to make sure everything's loaded. And so now at this point, we can always forget the syntax for GDB find. Let me, yes. Well, actually, let's search. Oh, that's a bit much. Oh, is that searching for? Yeah, no, that's not what we're wanting. Okay. Let's see. Why is that not finding it? That's a very bizarre thing. I just the ed string that we see here in the binary, right? This is in the program somewhere. However, it is not showing up in Binja at all. Because this is the dwarf debugging symbols. That's why. Binja does not show those. That's fun.
They are loaded into memory.
Yeah, no, so this is the thing. The way, a brief side note as to why this is happening. So ELFs, which are the binary format that Linux binaries are packed in, for lack of a better terminology, is sort of weird with how it handles some things. It's also very similar in others, but it's sort of weird. In this case, what we're seeing here is you can see this is a lot of like human readable things, including you'll notice up here crtstuff.c. Like this is an actual like file name that's been encoded in here. And these are what are called dwarf debugging symbols, which is basically this is how GDB can extract information about like this function has, or like there's a global variable called buff here, or like this function has these stack locals. which these end up being in program memory when the binaries run. However, Binary Ninja is actually just showing us what it sees as the stuff loaded into memory, which is apparently not correct. It's not showing us everything, as you can see, right? There's more here. We can take an educated guess as to where these are going to be, though. Usually, it's a fair assumption that if you go to the address, let's see, this was 1975. So if we GDB main, then if we look at 3 plus 0x1975, no, that is not. Oh, doing that. All right. So, fork mode. Also, while I'm at it, I might as well mention this. Some people were having issues with Get Got Good that were where you would basically see this. The program would appear to execute normally once, and then when you tried to run it again, you would just see starting program bin date, and then it would immediately exit. This is because everybody had the follow fork mode set to child, which I think is actually just the default. But regardless, the reason this is happening is because bin date is being run. GDB is actually following execution into bin date. That's immediately exiting once it's printed out the date, and then GDB is like, okay, everything's done, right? So you need to reset this follow fork mode parent to make things hopefully not break entirely. Parent remain run. Okay, now we should be able to do this. There we go. Interesting. Yeah, no, it's not there. Let's access 601. Okay, so 975. Nope. Interesting. Well, those should be in the binary somewhere, so that we aren't burning too much more time. I'm just going to cheat here and put a nice car star, or car, let's just call this foo, sh. Let's see. Oh, whoops. Let's actually just drop that here. Just be very nice. Okay. Now we know that main will have bin sh somewhere. Ed, again, you could use this with the ed trick and just launch ed and then bang bin sh off of that. But whatever, we can't find it immediately. Not worth spending too much time on for the sake of a demonstration. So we now know that this address 400804 will contain bin sh. However, again, if we run this, nothing is effectively changed. If we still can't just magically get bin sh because the string is there in the binary, but the system is still not being called on it. So now let's actually get back to ROPing. At this point, like I said, we've filled up our stack locals and our saved RBP. So now what we need to do is find an instruction, a ROP gadget, that will allow us to take something that we control, in this case a pointer to the string bin sh, and move that into RDI. Because RDI, again, it's the first argument to functions on the 64-bit calling convention. And so when we then call system, RDI will be set to our bin sh string, and all will be well. So to do this again, there's a couple of different utilities. I have ROP gadget installed. So we're going to say, hey, ROP gadget, find all of the gadgets in main. And this is what the output looks like. Notably for us, though, we have these types of instructions, all these pops. And even more noticeably, we have a very nice pop RDI ret. And so what this is going to do, right, as advertised, it's going to take the next thing on the stack, pop it into the register RDI, and then return. So we can chain this with a call to system and our known bin sh location to to ROP around. So, and I actually forgot to get the address of that. This was here. So our gadget is going to be at that address. But then again, this is now going to pop something off of the stack, and this is all just overflowing up the stack. So we now need to actually give it the pointer that we want to pop into RDI. So that was 400804. And so now at this point, yes, sorry. Yes. So I use a utility, it's just called ROP Gadget. This is the output. What was the exact question again, sorry? Oh, yeah. So it shows you all the things that it thinks might be useful. I don't think there's a set format of everything that it shows, but generally what it's looking for is some relatively few instructions followed by a red. You'll notice all these end with the red, because when you're ROPing around, you're creating this big list of stack frames, basically, and so you're returning to each one of them so that you can control where it goes next. So in this case, most of the time, these pop gadgets are super useful, and they're really abundant, because so first of all, pops are usually, I believe these end up being 1-byte instructions, a lot of them, so it just happens to be, it's just short. But more importantly, popping out, putting things into registers is a very common thing. So yeah, you'll basically see some gadget that can pop into the first 2 arguments to RDI and RSI basically all the time. These 2 basically will almost always exist. I don't think I've ever seen them not exist. And then you'll also see a lot of these just R14, 12, 13, 14, 15. Those aren't super useful, because we don't have, nothing really uses those. However, they're good intermediary steps. But regardless. So if we go back to our script, we now have the actual pop gadget. So I like to label these as well. Pop RDI, and then this is the pointer to binsh. And now we just need to say, okay, once the pop returns, what we're just about to add is where it's going to go next. So at this point, RDI is already loaded with pointer to binsh, so we're good to just call system. So we can just find system and 400530, and that should basically do it. We need to actually, we need to actually send it to the process, and I believe I left, yeah, so we also just need to give this a valid address to read. This will become a lot more useful here in a second, but we don't care about it right now. We'll just send line 0x400000, which again is basically where 64-bit binaries get loaded by default. So it's a fair bet of the thing that's going to be readable. And then we're going to send our ROP chain in. And then in theory, we should have a shell. So let's see if this works. And UOF, so presumably not. Let's hop into GDB and actually debug this. And this is dark. All right. So let's see, where are we here? We're in main. 6. Let's actually just set a breakpoint right before the return. One thing that's very useful in general is to just set a breakpoint on the very last return from whatever function you end up ROPing in. Because again, ret's what actually does, what kicks off the ROP chain, if you will. So we can set a breakpoint here. And all right, so okay, bye now. So you can see we're going to, this thing get eaten up. Let's see. So you can see, first of all, right here on the stack where we're just about to jump to is our call to system, right? So we got that part right at least. But for some reason, this stuff seemingly did not get sent. Or did not get... Let me try something else really quickly. So we're in fgets. Let me break point here. Not go to address. Don't want that. All right. So our read has just returned. Our buffer should be full, with the data that we put in. Sorry, that's the wrong one. This is the call that we want. We want just after that. Okay, now at this point, this should be correctly set. So we can see we have all of our A's, so that looks encouraging. But I know what the issue is. Yes, so I was exactly just the wrong amount off. As we talked about it here, this was effectively doing that. That's not, there we go. So the buffer itself is only 32 bytes, and we only need to account for the saved RBP above that, right? Well, it turns out that, if we actually look at the disassembly, we're actually subtracting 30 from RSP. Why? This is probably for some alignment purposes. However, in this case, well, we now actually need to send x30As. Still need to send the 8 to fill up RBP, but now, theory, let's try this again. We should be better off. All right, that looks much better. So, yes, this is, I guess, a good thing. In general, you are only going to have the assembly, and the assembly doesn't lie to you. The compiler can do weird stuff. So, anyways, yes, that's a very, very basic example of a ROP chain. We have the single gadget of pop RDI, a known BNSH pointer, and a known system, right? So let's make this a little bit more complicated. Let's remove some things from our code. So let's not have system anymore. We'll leave the string to BNSH for just a minute, but then we'll get rid of that as well. But let me recompile, and now we don't have system. Yeah, I got rid of the reference. So what are we to do? Well, we have an address that, this is demonstrating a vulnerability where we could get some kind of information leak or an arbitrary read. So, as we talked about last week, the GOT is full of addresses, whether they be unresolved to local stubs to resolve them, or resolved libc functions. So the first place that you always want to look for, functions, if you have a read like this, is the GOT, right? It's going to be at a static address, and it's going to give you a leak of libc. So let me copy this new binary out to Binja, not linking, and we'll take a look at the GOT over here. No. Okay. So at the point that we call this this fgets to overflow, we're going to have, well, actually, no. Printf, okay. At this point where there it is. At this puts call, this is what shows us the result from the leak that we asked for. We're going to have at least 3 symbols resolved. Printf has to be resolved because we already called it. Same with fgets and string to unsigned long. There will be a few others that we'll see that are going to be resolved as soon as the program is running because of how programs actually start up. You've probably seen this function up here, libc start main. As the name implies, this is in libc, and it starts the program's main. However, though, again, it's in libc, right? And this is also in the GOT, so it's going to be resolved. So this is always a fair address to pull from too. Doesn't really matter. Any of these should work just fine. So if we look at the GOT itself, we can see how it's ordered. In this case, we can actually, let's use printf. Printf actually probably isn't the best candidate. Let's use libc star main, sure, why not? So the address hex 601.028 is going to be a resolved libc address for libc start main. So if we come over here again and we run the program with 601.028, you can see it gives us some weird output, right? This is because we're just putting out an address as if it were a string. Most of the characters in libc address, like in a high address space where libc lives, are not printable. A lot of them are like 7F, FF, sometimes another FF, and so you generally won't see printable stuff. However, you'll get pretty used to pretty quickly seeing, if you see any like garbage characters, those are usually like, don't ignore them thinking that something glitched, right? Like this is a very good sign. This usually means you're leaking something, or in general, you're reading uninitialized, you're either reading uninitialized data, or you're reading some data that maybe isn't what you thought it is. You know, perhaps it's a pointer, it could be a libc pointer, it could be a stack pointer, it could be a heap pointer, it could be all kinds of things. But garbage data is something to really be looking out for now. So, if we go back with this, let's make a new ROP pi. We'll leave GTBN for now. So, in theory, unless this changed again, no, it is still hex 30, so this padding is still the same. But before we even actually get to the padding, you know, let's process out the leaked data. So I'm going to move this send line up here, just to make it a little bit more clear what's going on. And like I said, we're going to use 601.028, the GOT pointer, or the GOT entry for libc start main. If we now print of, I believe there is a line up here. So let's also just get rid of all that. So 2, okay, and continue through that. Why are you not moving along? Perhaps that's not correct. Let's also get rid of GDB for the time being. Ah, yes, right. So in this case, this was not actually a full line that we were receiving. We just need to receive until this like colon space that we saw. So now we 2. Okay, now it's just lying to me. What's going on? Let's receive until colon. Still does not work. Okay. Let's just immediately send line. That should be fair. Okay. Now, this looks very encouraging again. Like I mentioned, if you see this hex 7F that's up near high memory, which is usually where the stack and libc live, seeing that character is always a good sign. And in this case, you know, this is a completely resolved address. Now, how do we extract this? You know, as is, this is great, but in our ROP chain, we need to use this to get where the base of libc is, right? So where it's like the very top of where it's loaded, and then we can use that to re-offset to other functions that might be more interesting, right? So libc start main is great, but system is also really nice for our purposes. So if we can use this, convert it into, you know, a number that we can easily add and subtract with, subtract like a known offset to bring this back to the libc base, and then re-add the offset to system, let's say, this gets a lot more useful. So, as Josh mentioned, in Pwn Tools, there's P64, as we've been using, but there's also U64, which is the inverse. It takes a string like this and will convert it back into, it'll flip the indiness around, and then hex decode it into a number. Now, one thing that I really wish existed, but does not, and we still have to deal with it, is U64 requires exactly 8 bytes. You cannot send it, you know, a partial string like this. You know, you can see here we only have 1, 2, 3, 4, 5, 6 bytes, which is typical. we can't send it that. It'll error saying, hey, I need 8 bytes to work with. So the trick is usually just to forcefully suffix 2 null bytes to the right side of it. I really wish you didn't have to do that, but you do. So, but let's say we have our leak is going to be the contents of our receive line. We're going to then say, this is where knowing some Python stuff can get nice, because while you do want to make your code sort of readable, you want to make it reproducible, you do have to get sort of creative, for lack of a better word, with how you do string manipulation with this kind of stuff, especially since receive until : was not working. So in this case, we're going to just say, we're going to have our address be our leaked the entire string from the index of : space onwards, actually through -1, which means basically you take everything from : space onwards, except the last character, also truncate that off. So that'll get rid of the trailing new line, and we can print adder. Now that I said that, I think index is going to return the beginning of it. Yeah, it is. So this is where you just kind of have to get, it's sort of annoying to do string manipulation, whatever. You could also have this just be a constant offset, since you know what the message is going to be. This makes it a little bit more clear what's going on, but whatever. So now you can see at this point, this is good. We have 1, 2, 3, 4, 5 bytes. There we go. And so we can now start to, now we can actually use 64 this to turn this back into a number. But again, we need to add zeros onto the right side of the string, because again, little endian, the highest bytes are on the right, and all the zeros are at the right end of this. Print libc start main doesn't happen to end at an address ending in null null. You can see that for yourselves if you want, but you're almost always going to have to append 2 null bytes to addresses like this. So usually you can just do like that. Sometimes if you want to be nice, you can also just say plus equals a null byte times 8 minus the current length of adder. Either way, they should in theory do the same thing. And so now you can see we have, again in theory, a full 8 bytes worth of data that we can actually pass into U64. So adder is now the little endian 64-bit decoded version of the string. Now if we run this one more time, this is good. We have a number out of this. And if I open up another IPython window to show the hex value of that, 7f, 79, this looks reasonable. One telltale sign is functions in libc also always end up starting on a nicely aligned address at the end. So the very last nibble, this 0, is always going to be a 0. So if you see that and you see a 7f on the left side, you're probably good. You probably got all the decoding working. So we now have an address. This is great. Now we need to transform this into libc base. So we need to take this address for libc start main and figure out kind of a common point where libc is initially loaded. PwnTools is also really, really nice here, because what we can actually do, I believe I demoed this before, is you can actually just load entire binaries with this. So I need to find the exact path of what libc I'm using. Here it is. And so we can just load our entire libc. And then we can say, give me e.symbols of libc start main. And in theory, I realized I forgot to print that, but this will be a nice relative offset, because libc is all relatively loaded. So the elf loader here has no idea to know where the base is, so it's just going to give you an offset from where the base should be. So we can now extract, if we subtract, we'll say base is adder minus e.symbols of libc start main, and print base. So at this point, so I can already tell that looks a little bit weird. This doesn't look quite right. libc is always going to get loaded at, actually could be possible. It's always going to be loaded at an address where usually at least 3 of the rightmost nibbles are zeros. It's going to be somewhat relatively nicely aligned. This looks sort of reasonable. If we want to, we can also, I guess GDB I don't have open. We can also confirm this in GDB. If I bring gdb.attach p back. Alright, so we can now info proc map, which is information for the process mappings. We can see our expected libc address is this, which is 7f0479, and we can see in reality, the terminal's wrapping here, which makes it a little bit annoying to read. Oh, nope, come back. Okay, so here is the very first entry in our libc loaded, and 7f04, that looks correct, right? These two are the same. If we copy it, look good, right? So we now reliably have our libc base address. So now with this in hand, we can take our base, re-add an offset to something that might be more interesting. So let's say system is going to be our base plus e.symbols of system. And so now at this point, we're basically back where we were last time, where we have an address for system, an address for binsh, and our ROP gadget, right? So let me get our new gadget address for main. Like I said again, this pop RDI you'll like always find somewhere. And so just make a note of that. So now we just need to form our chain together again. So we're going to start by filling up our buffer with hex 30As, and then another to fill up our saved base pointer. We now need to append our gadget of pop RDI, and then again this is going to take the next thing off the stack and put it into RDI, so we need to find our pointer to binsh. 400794, and then at this point we should be good to just jump to system again. We shouldn't need that, and let's try it out. Exited normally. So it didn't crash, but we also didn't get a shell out of it, which I believe is because I forgot to actually send the chain. Yep. So it does help if you actually send everything you just worked so hard to get. Continue. There's our shell. All right. So at this point, we've leaked a libc address to find where libc start main is, subtracted off of that to find our base, re-added to that to find system's address, and then use that in a very simple one gadget ROP chain. So we can, I guess we'll like take this to the last step for the day, which is we don't have binsh anymore. All we have is a single leak and an overflow that we can start ROPing on. So we'll compile this, and now we really don't need to change up much at all in our code, because as Josh said, binsh is in libc, right? Like it's going to be there somewhere. So we can do this a couple of ways. You can use GDB's find to find strings in memory, or we can again take kind of an educated guess with libc. Let's actually linux. Where are you? x86, 64, Linux, libc. 6. All right, so this is the entire binary open. We'll literally just search for. There you go. We'll literally just search for binsh as text in here. Magically, wow, look, there it is. All right. I'm not sure this is going to be the case, but let's just try saying this is going to be libc base plus the relative offset in the binary. I don't know if that's going to be true, but again, usually it's somewhere around there. So system is now here, and we're just going to say binsh is base plus 0x18CD17. 18CD17. Did I copy that? Yes. Wait. I just realized I clicked off of it. 18CD17. Looks good. All right. So the only change here is that now instead of using our local binsh, we're going to use the binsh as it appears in libc. Let's see if it works. If it doesn't work, then we'll use GDB here. Nope, did not work. So, oh, the stack changed. That would do it. So, let's just really quickly find what the new stack size is. Now it's 20. There it is. So this is now going to be, there it is, 20. And if we continue, oh, still crashed. But now we're somewhere really weird, right? This looks, we're in this under FI&I thing that doesn't seem right. So now let's take a step back and let's like go through and maybe find libc more properly. To do this, I'm going to just use GDB. We know, again, we can find the libc base in the debugger with just info proc map. And I always have to look up the format GDB find string memory. GDB uses sort of a weird syntax, and I realize you guys probably can't see this. Okay, so it's find. So the syntax appears to be find start address, comma, end address, which is going to be the end of the last like libc entry that we see here. So this, and then our string. Cool, there, it found one. All right. So at this point, we need to just find the actual offset from the libc base that we have, minus this, 18CD17. Okay, so our educated guess appears to actually have been correct, of 18CD17. So now we need to, whoops, now we need to find, now we need to actually like do a little bit more work to figure out why this is still crashing. Base, we know we were leaking correctly. We can verify this again, just wrap this in a hex call. It makes it a little bit easier to see. This change, that should still be the same. The gadget. The gadget has also changed. Let's ROP gadget again. Binary main. Here it is this time, 407.23. I'll change by 10 again. Okay. And in theory, yep. Cool. So we've now taken a program that has no system, no binsh, and made it spawn binsh. So, you look like you were about to say something?
Do you have the magic gadget finder on your box?
I do. Okay. So, yes, this is a fun thing with 64-bit binaries. libc, I think I actually mentioned this at some point a couple talks back. libc actually has some addresses in it that will do all of that basically for us. Where as soon as you find libc base, you can just jump to one of these addresses and it sets up a call to binsh and calls it for you. There's a few of these finders online, however, they really aren't that good. We actually had to patch this one to work well.
Is this the one that uses Radar 2?
This is,
Yeah.
yes. Yes. So this is, this is just sort of for fun. We don't really expect you all to use these. You can if you want to, but again, at least the one that we found easily on GitHub was really broken because they didn't know how to use Radar at all. So yeah, it just like did not find some very obvious ones, but I'll just show you it working just for fun. So you basically just tell it you just tell this program that I'm on 64-bit and here's the libc that I'm using. Again, with a lot of challenges that involve doing something like this, they'll give you libc so you know exactly which version they're using. And then it takes a little while. These programs can work in a variety of ways. It also doesn't help because I think Radar is just slow because it's doing full analysis on libc, which is like a couple megs. Yeah.
Can't we just write the string in sh now?
So this is a very good point. So you can. However, the trick is you're writing on the stack, right? You don't know where the stack is because the stack also moves around in high memory. So it is possible to leak a stack address, though. This is, maybe we'll do this for homework at some point, but yes, you can definitely do that. The trick is, like I said, though, you need you need the pointer to binsh. And to know that, you need to know where you are on the stack. To know that, you need to know where the stack is, but that changes every time you run the program.
So doesn't the pop RID command just pops the whatever the contents of?
Yes, it pops the contents. It pops the next 8 bytes into it. It does not pop the address of the next 8 bytes. It actually moves like if I have the sequence hex 1, 2, 3, 4, 5, 6, 7, 8. The register will then actually contain 1, 2, 3, 4, 5, 6, 7, 8. It's not an address to that point on the stack.
If you get very lucky, you can get stuff that lets you move RSP into another register, and then you can do math with it.
Yeah.
But in like the smallish binaries we get in CPS, it doesn't happen that often. But maybe you get lucky. It's also quite a chore to do math inside of a ROP. And as much as possible, you want to avoid it.
So
just because, especially again, these binaries are kind of small, and you're somewhat limited in the edges you get. It's basically a recipe to have a bad time. If you decide you're going to do math inside ROP.
There are also some tricks that you can do if you want to do this, where you can actually set up basically. You can set up a call to. Let's see, how do these usually work? You can set up a call to read, to basically reread as whatever data you want. And where am I going with this? There is a trick with, what is it? Basically what you can do is you can get a stack address. With ROP, you can actually you can set up a call to puts to print a stack address that you can then reuse later in your exploit. These are incredibly rare, but basically what you're doing is you're setting up a call to puts to print a stack address. And then at that point, you can then chain into read to read in more stuff to overflow. And then when you return from that read, you're now returning into the stuff that you just read in, which can have knowledge of the stack address that you leaked. So this is one of the things with ROP is you can get these like weird layers of you can leak knowledge out, and then even though you've sent off some of your chain already, you can set up a call to read in more of the chain with knowledge that you gained from the first part of the chain. So you can do weird stuff like that. Also, occasionally you just get really lucky and you get like a push RSP ret, and then so you can just push RSP to the stack and then pop that into another register, and then you can now just use that. It's incredibly
Push RSP ret would jump to the stack.
This is true. What is it? No, it's a sequence of some weird pushes. I've seen them before though, because
push another
maybe it's actually just a move.
You do a gadget before that takes control of that other register to point it to your next gadget.
Yeah, basically, so the trick with ROP ends up being finding the right sequence of these. Sometimes you can also find ones where you could move RSP in some intermediary register, then push that and then pop that back, or it's some really weird combinations of stuff. But yes, so to answer your original question, yes, you can ROP if you just if you have an address of your stack, and then you can do computations to figure out where binsh is. But at the same time, usually you already have some kind of libc leak because you're going to jump into libc at some point, and so you can just use binsh in there. It's not always guaranteed, of course, because you can ROP back to God entries too, right? Just more code. You can ROP back into the linker. But yeah.
There are also other more effective ways to do this. There's a relatively new technique called SIGROP, which is really cool, which basically just you need is a syscall and control of RAX. We're not going to get into that in this class, but it's fun further reading. At this point, you have everything you need to know to understand why it's awesome.
So, anyways, yeah, so at some point in our conversation, the magic gadget finder returned and it found 3 of these so-called magic gadgets. And so we can take, in theory, any of these. Again, it's not perfect. Let me just, sure, move ROP for pi. Okay. So now instead of doing this, what we can do is we can just say our magic is our base address plus this, and then you literally just chain straight into magic. Nothing else needed. And sometimes the program returns bad data. It looks like it did that time. Usually you just have to try a few of them. One of them will eventually work. Try that one. Sigabort. Nope. ROP for...
Chance we get unlucky here. Broken.
This is also quite possible. Let's see, the last one. Will it work? It looks like it worked, yeah. There we go. So, yeah. So, again, these occur almost every time you get a libc now. At least this is Ubuntu 16.04. Most competition binaries are run on that.
I also want to note, as an interesting curiosity, about actually almost exactly 2 years ago, this technique was basically entirely unknown. This was like a secret that maybe like a couple dozen people in the world knew, and it is now a pretty common trick.
Because it saves you so much time, right? You can
So,
just
like,
jump
if
to
you
an
think,
address and
like,
you're done.
Wow, this seems pretty crafty. This is basically state of the art in exploitation. So we're in the modern day of like we were working our way up from like the 1980s up till now, and we're now in the modern day and finding new techniques.
But yeah, so that basically covers basic ROP. Again, the challenge with ROP is just finding the right gadgets in the right order. Usually the rule with this is the bigger the binary, the better, right? If you have like a meg binary that they give you, you're going to find a lot of gadgets in there. But even just for very simple binary that uses printf, fgets, puts, and that's it, we can use this because there's an overflow to get shell, right? So, yeah, this gets very, very, how do I want to say this? This can get very difficult very quick because of finding the right gadgets to use. However, it's very cool, right? You know, we have this binary that has no functions, no system, no binsh, and we just got all of those out of it with a single read and an overflow. Yeah, so any questions about any of the 4 ROP things that we just went through, starting with all local and then working into libc? Questions about how I got a number, or how some part of a script works, or anything like that.
What was that, the address?
What, like finding it, or what exactly?
What was that?
So, right, so the address itself, what is this? Basically, it just so happens that, and we can actually look at this, let's see, go to lib, 64 libc.so.6, and let's actually just look at libc and binja. This might take a while to analyze, but, this is symlink. Alright, so I'm going to give that just a second. Analyze F1117. So it just so happens that at this address in libc, there is a move of some environment stuff into REX, and then notably here we have a load of binsh into RDI. In this case, it's pulling some environment variable out into RDX and then calling execv, which is just it's similar to system, right? So this just happens to be here in libc. Who knows what function this is in? It's not labeled. So this is in some subroutine used by some libc function that happens to call binsh. And there are multiple of these. Some of the more advanced magic gadget finders will actually say they can find bigger chains, and then they can say, as long as you have this, this, and this in your registers, it can like find its way down the correct like control flow path. This one is very simple. I think it's basically just looking for some load of binsh into RDI, and then some few number of executions later, a call to execv, exec system, one of those types of functions. But yeah, so all the magic addresses is just doing that load call exec for us. So, yeah. Yep. So that's all we had to do, because again, like at this point, this is a self-contained snippet, right? Everything in here just works. There's no references to RBP, which we might have had to overwrite, and RAX is just a load from an environment. RSP is not corrupted at this point, and then this is a relative load within libc. So everything's self-contained and just works. So, yeah, yes. Yes. Yeah. Yeah. We will provide it.
Fingerprinting? Really cool.
Sure. Yeah, sure. So let's see. Let me modify this really quickly. So say that we have. Oops, not that. There we go. Oh, there we go. Okay. So say we now have the ability to leak 2 addresses. So at this point, we will have at least 2 things resolved. We'll definitely have libc start main, and with the second, second leak, we'll have printf, fgets, and puts resolved. So if we take this binary out over here, please, ninja main. So if we look at the got table for this, just find a function, go here. So if we can leak some of these addresses, we can use a libc fingerprinter to just figure out what libc we're using. So like I said, at this point, at the point of the second resolution, I think all of these symbols should be resolved. So we'll just pick 2. Sure. Import functions, create our process again. And we're now going to send line of just hex. Let's just use puts and libc start main. Sure. Yeah, that's why I modified main to take 2. Yeah. Actually, you know what? Let me steal this code out of here. Okay, so we're going to take 028, which is libc start main, and we're going to. So this is going to be libc sm, and then don't think I put a new line in there, so we should be good to just repeat this exact code chunk again, except this time with 1.8, and 1.8 is puts. So we'll say puts, and then we're going to print hex libc sm hex puts. Make sure this works. All right. Yep. So those look like 2 good resolved addresses. What's a good? I forget the name. BLU what? BLU. Dot what? Sure. All right. JS. All right. So this was I already forgot. Yeah. So that was start main, and then the other one was puts. So there's start main, and I believe that ends up showing up as IO puts. Yep. Here's IO puts and find. Oh, and there you go. There's two binaries, and so you can just try both of those for magic addresses. You know, if we have another one, we can just add more, and I'll constrain it further, right? You generally only need two, though. That'll get you 1 or 2 ellipses, and then you're good to go off that, right? You know, you can try both relatively easily.
This is not necessarily complete if they run on their CTF on like a really weird Linux distribution. Maybe you won't get
But
it.
it's going.
But they run it on like every version of Ubuntu ever, and I think every version of like Arch ever, and probably every version of Fedora ever, and that's basically everything you'll see on the normal, on like basically the internet. So like maybe you'll get unlucky, but whatever.
Does it use the offset between the 2 functions?
Yeah.
Yeah, so you can do all kinds of fun when you can start leaking libc and pull functions out of that. So, yeah, any other questions? Otherwise, I believe we're coming up on time. So, any other questions about ROPing in general, code I wrote, offsets, magic addresses, anything like that? Going once, going twice? No, all right.
Okay, final reminders, we're putting up midterm grades. Add drop deadline is the 6th, make your decisions. And homework's gonna go up tonight, and you have until 10 p.m., which is in like an hour and a half to
Yes.
submit
Brutus.
Cool.
All right, have a good weekend.
Good one, guys.
Peace.